Hello class 12. In today's video we are going to learn about, first of all, something called power of a lens. Now you've studied this in your class 10 also. The power of a lens is basically the reciprocal of the focal length measured in meters, but the focal length has to be measured in meters. So power P is the reciprocal of the focal length, that is 1 upon focal length, and this focal length has to be measured in meter. So this is how we define power of a lens. Now the unit that we use to measure power of a lens is diopter. It also happens to be the SI unit of power. Now how do you define a diopter? A diopter is the power of a lens having focal length equal to 1 meter. Diopter is the power of a lens having focal length equal to 1 meter. So this is about power of a lens. Do remember the unit diopter. It is represented by a capital D, by the way. Let me write it here. So capital D represents diopter, remember. Now let us talk about combination of lenses. So first of all, we talk about two thin convex lenses, as you can see in the picture, in contact. And we will see what will be the combined focal length of these two lenses. That is the combination of these two lenses. What will be the focal length like? We are going to see that, and of course thereby we will also see the power of the combination of these two lenses. So we have lens L1 and lens L2. They are placed in contact, and we have a point object O placed at a point here on the principal axis. Now if this lens L2 was not there, what is this picture telling us is, if this lens L2 is not there, then the image of the object O is formed by lens L1 alone, because L2 is not there. So if L2 is not there, then the image of this object O is formed by lens L1 alone at this point I dash. So the dashed lines over here are showing the position of the image I dash of the object O, of course, in absence of lens L2. So I dash, you can say, is like the virtual image now. Virtual meaning in the sense that this actually is not there, this image is not there, but it would have been there if L2 was not there, lens L2 was not there. But since L2 is there, actually there, okay, so the eventual final image is formed at point I. So U is the position of the object O, distance of the object O from lens L1. V is the distance of the final image, actual image that is formed by these two combination. So V is the distance of the final image I from lens L2, and V dash is the distance of the non-existent image actually from lens L1. So if L2 was not there, I dash was the image that would have been formed. So distance of I dash from lens L1 is V dash. Okay, so that is what I've mentioned here. So let two thin lenses L1, L2 having respective focal lengths f1 and f2. So f1 is the focal length of L1, f2 is the focal length of lens L2, and they are placed in contact. So use the distance of point object O from L1. V dash is the distance of I dash from L1. So distance of I dash from lens L1 is V dash, and the distance of the actual image I that is formed, okay, is V from measured from lens L2. So then after, so in absence of lens L2, the image of the object O, would be formed by L1 alone. That is exactly what I've written at I dash. Okay, so in which case, applying lens formula, what we get is for lens L1, if L2 was not there, so for image I dash formed by lens L1, by this lens L1 in absence of L2, so applying lens formula for the first lens alone, we would get 1 by the image distance minus 1 by the object distance is equal to 1 upon the focal length of the first lens. So this is applying lens formula, which is 1 by V minus 1 by U, which is equal to 1 upon F. That is the general form. So for image I dash formed, the image distance will be V dash in absence of L2, remember. So this is the lens formula, and that is our equation number 1. Now, the reality is we assumed the equation 1 we got, this equation 1 we got is assuming lens L2 is not there. But lens L2 actually is there. Okay. So, for lens L2 now, so we have, so to say, initially dealt with refraction taking place through the first lens. Okay. Now, for refraction taking place through the second lens, here you can see refraction taking place initially from the first lens and then refraction taking place through the second lens. So we've dealt with refraction taking place through the first lens. Now for refraction taking place through the second lens, I dash acts as the object and I is the final image. Okay, so now that is what I've written here also. I dash now acts as the virtual object for lens L2, which forms final image I, and for therefore refraction taking place through the second lens, using lens formula, we get 1 by V, which is the final distance of the final image, as you can see, minus 1 by V dash. Now 1 by V, why? This is the object now. This is the object distance now. V dash is the object distance for the second lens, equal to 1 by f2, the focal length of the second lens. Now, V dash, as you can see, is the distance of I dash measured from lens L1 actually. Okay. But here, since we are considering two thin lenses, so the distance between the optical centers of the two lenses, it's negligible. We've, neglected the distance between the two lenses since they are two thin lenses. So V dash also is, we've considered, also is the distance of I dash from L2 also. So that is why V dash is now the object distance. This acts as the virtual object for lens L2. So therefore, V dash is the object distance for lens L1. So 1 by image distance for lens L2 minus 1 by object distance for lens L2 equal to 1 by focal length of the second lens L2, of course. So now this is equation number 2 and we already have our equation number 1 here. So combining these two equations, adding equations 1 and 2, we get 1 by V dash minus 1 by U. This is what we get from equation 1, left hand side of equation 1, plus 1 by V minus 1 by V dash. As you can see, that is the left hand side of equation 2, equal to 1 by F1 plus 1 by F2. The right hand sides, adding the right hand sides of equations 1 and 2. So 1 by V dash and minus 1 by V dash, they cancel each other out. You can check the mathematics yourself, and thereby we get 1 by V minus 1 by U equal to 1 by F1 plus 1 by F2. That is our equation number 3. Now, what do we assume then after? Now, if these two lenses, if instead of these two lenses, what we do is we use a single lens, in which case, for the same object distance, for the same object, here is the single lens, say for example, replacing those two combined lenses by a single lens, such that if the object is placed at U, then the image is formed at V, like these two combination of lenses, this combination is doing. If the object is placed at U for this combination, the final image is being formed at V. Okay. So now instead of these two lenses, what we are doing is we are using a single lens. In this case also, in case of the single lens also, this is a special kind of lens, in which case what happens is, for the same object distance, we get the same image distance. The image is formed at distance V from the lens itself. So this special lens is what is called your equivalent lens. And if the focal length of equivalent lens is F, then for this equivalent lens, for this case, we get 1 by V minus 1 by U equal to 1 by F using lens formula. That's equation number 4. So the left hand sides, as you can see, of equation number 3 and equation number 4, they are the same. This is for the combination of two lenses. This is for the equivalent lens. So from equations 3 and 4, we get 1 by F1 plus 1 by F2 is equal to 1 by F. That is the reciprocal of the focal length of the first lens plus the reciprocal of focal length of the second lens is the reciprocal of the focal length of the equivalent lens. Or so to say, the power P1 of the first lens plus power p2 of the second lens is equal to the power p of the equivalent lens, or that of the combination of two lenses. P is the power of the combination of two lenses. So we can write this also. Now, one small thing. So the power of the combined lenses is equal to the addition, the sum of the power of the first lens and the second lens. Now, if lens L2 is concave, so here we have shown the two lenses to be convex. Now, if the second lens L2 was, concave, then the focal length of the concave lens F2, this focal length will be negative, because the focal length of a concave lens is negative. It's on the left hand side. The focal point is on the left hand side of the optical center for concave lens. So therefore, the focal length of concave lenses are negative. So therefore, this equation becomes 1 by f1. Let me place it properly. Yeah, 1 by f1 minus 1 by f2 is equal to 1 by f. The focal length of the second lens is negative. So we get f is f1 plus f2 divided by f2 minus f1. You can check the mathematics, simple mathematics. Okay. Now if f1 is greater than f2, if this f1 is greater than f2, then the denominator is negative, and on the whole, the combined focal length is negative. So f is negative. So to say, the combination of a convex lens and a concave lens, in case the focal length of the convex lens is greater, f1 is greater than f2, then the combination behaves like a concave lens, remember. Now, if f1 is greater than f2, f1 is lesser than f2, that is f2 is greater than f1, then the denominator is positive. So f on the whole becomes positive. So f is positive, that is the combination behaves like a convex lens, remember. And finally, if f1 and f2, they are equal, if f1 is equal to f2, if f1 is equal to f2, if f1 and f2 are the same, then the denominator becomes 0. So anything divided by 0 is infinite. So f is infinite. And the combination, focal length is infinity, means the combination behaves like a plane mirror simply. Because the focal length of a plane mirror is infinite, remember. So focal length is infinity means you have to understand that the combination behaves like a plane mirror. So this is all for this video. We will meet again in the next video. Thank you all so much.